Welcome to part 2 of my lectures on the motion in a central force field. First, a quick recapitulation of whatever we have done in the previous lecture. Firstly, we had defined a central force field, which is a field of force whose magnitude depends only on the distance from a fixed point and is always directed either towards or away from that fixed point. And by choosing that fixed point, the center of the force, as the origin, which of course is the obvious choice, we have an expression for the force vector. That is, it's equal to small f of r times r hat, where r hat is a unit radial vector. Now, the most common situation where we see central force field motion is really in a two-body problem. Two structureless bodies interacting only among each other would essentially be interacting through a mutual force which is of the central kind, and by reducing the two-body problem to an effective one-body problem involving the separation vector small r, r1 vector minus r2 vector, you end up with the equation mu small r double dot equals f of r r hat, where mu is the reduced mass m1 m2 by m1 plus m2. We had seen that the angular momentum L, which is actually the angular momentum of the system as observed by an observer fixed to the center of mass of the system, is given by mu times r cross v, happens to be a conserved quantity. And an immediate consequence of that conservation law was that the motion must be planar and the areal velocity, the rate at which the radius vector sweeps out an area, is a constant. And because it was planar, we could actually use standard polar coordinates in a plane, for which we had derived the expressions for the velocities, radial and cross-radial components, namely r dot and r theta dot. Also, we had figured out the accelerations, radial and cross-radial components, r double dot minus r theta dot square, and 2r dot theta dot plus r theta double dot respectively. And the equation of motion which you get for a central force field problem in this case is mu times r double dot minus r theta dot square equals f of r, and the cross-radial equation mu times twice r dot theta dot plus r theta double dot equals 0. The second equation immediately gives rise to the conserved quantity r square theta dot, but the fact is not novel in the sense that we already knew that this is a conserved quantity because this is nothing but the magnitude of the angular momentum per unit reduced mass, small l over mu. The importance of this equation is that by using the fact that theta dot equals L over mu r square, we can change the radial equation into an equation which involves only r, that is, decouple the theta away from it. In fact, if you just substitute theta dot equals L over mu r square here and move the resulting term to the other side, you end up with this equation for the radial coordinate, mu r double dot equals f of r plus L square over mu r cube. So this is exactly like the equation of motion that a particle moving in one dimension would obey, except for the fact that in addition to the force Fr, the actual force, there is an effective additional force given by L square over mu r cube. Now this L square over mu r cube is often called an centrifugal barrier term, and the reason behind the name should not be hard to find. If you just use the fact that L, the angular momentum, at least the magnitude of the angular momentum, is actually equal to mu r square theta dot, then L square over mu r cube, this fictitious additional force, is simply mu r square theta dot whole square divided by mu r cube. After a few cancellations, you get mu r theta dot square, which should be familiar to us in the form mu omega square r. the standard centrifugal force which you get in a rotating frame. Now, the fact that you have a centrifugal force here should not be hard to understand. Basically, if you consider the radial motion and radial motion alone, you would essentially be thinking of an observer who is keeping on turning so that the particle is always straight along its line of sight. So this is really a rotating observer we are talking about here. And the existence of a pseudo force in the form of a centrifugal force is really not unexpected. As we have already said, the fact that r square theta dot is conserved is not really a novel fact. It is really the conservation of angular momentum in disguise. There does happen to be another conserved quantity for this particular problem though. And it's obvious what it is. The force here, f of r hat, is a conservative force, and therefore you would expect total energy to be conserved. Now, since f vector in this particular case is conservative, it should admit of a potential energy. You need the potential energy in order to be able to talk about conservation of energy. The potential energy is simply given by negative of the integral of f dot dr from some initial arbitrarily chosen position vector r0 to the final position r where we want u. Strictly speaking, I should perhaps use primes on f of r prime dot dr prime, because this is really a dummy variable of integration, whereas r is the final location where we are trying to find out the potential. One important thing is the potential exists only if the integral here depended only on the initial and the final points and not on the path taken. Now, by using the fact that f vector is given by f of r hat, it's very easy to see that this becomes f r prime dr prime's integral with a minus sign outside from r0 to r. The dr prime here is simply nothing but r hat prime dot dr prime, which comes out here. And by carrying out the integral, which is obviously independent of the path, this is just an ordinary integral in one variable, you should end up with a u which depends only on r and not on the full vectorial nature of r. That is, it does not depend on the direction of r, depends only on the magnitude. Since the problem of a central force is essentially spherically symmetric, this is what we would expect anyway. Of course, u depends also nominally on r0, but r0 is fixed once and for all, and therefore we will not bother about u's dependence on this. But u's dependence on small r is going to be very, very important in analyzing the motion. Now, we know for systems which admit of a potential energy, the total mechanical energy is the conserved quantity. And the total mechanical energy is simply, in this case, half mu times v square plus u of r. This is the so-called conserved energy, capital E. Now, the v here is of course the full velocity, two-dimensional velocity of the particle concerned. However, we can easily rewrite this by breaking the velocity up into its radial component Vr equals r dot and cross-radial component V theta equals r theta dot. So V square is nothing but r dot square plus r theta dot whole square. So the expression becomes half mu r dot square plus r square theta dot square plus u of r equals c. What makes this very, very useful for us is obviously the fact that we already know that theta dot is L over mu r square. And if you just plug this in here, what we see is that the total energy can be written down as half mu r dot square plus u of r plus this term, which can now be written entirely in terms of r. So the conservation of energy equation essentially ends up looking like the conservation of energy equation for a particle moving in one dimension. Just like there you would have half mx dot square plus u of x equals a constant, that would be the energy conservation equation in one dimension. Here you have half mu r dot square plus this whole thing which is dependent on r and r alone. There is no theta dependence in this term. The overall sum has to be equal to the total energy E, and if you consider this to be the effective potential energy for radial motion, this exactly becomes the same equation as this, except that u has been changed to u plus L square by 2 mu r square. One important point has to be borne in mind that the effective potential here, u effective, does not depend only on the system. U depends only on what system you are talking about. The u effective also depends on the initial conditions simply because the value of L, the magnitude of the angular momentum, will depend on what initial position vector and what initial velocity the particle had. So, depending on your initial conditions, the effective potential would change even for the same physical system. That has to be borne in mind. But with that in mind, this problem is essentially exactly the same as the motion of a particle in one dimension, which is something we know how to handle. So the radial motion has essentially been reduced to a standard problem for one-dimensional motion. In fact, this extra piece in the potential is also pretty easy to understand. The effective force that you would get from the effective potential is nothing but minus ddr of this. Again, this is effectively one-dimensional, and just like in one dimension, the force is given by minus du dx. Here it will be given by minus ddr of u effective r. But u effective being ur plus L square by 2 mu r square, this breaks up into two pieces. Minus du dr, which is the actual force magnitude, minus ddr of L square by 2 mu r square. And lo and behold, what comes out of this, the effective force, is our familiar formula. F of r coming from minus du dr, and this thing gives you the L square by mu r cube, the centrifugal barrier force or repulsive centrifugal force. The L square by 2 mu r square term in the effective potential is, by the same token, called the centrifugal barrier potential. Now, as we will soon see, the idea of the effective potential coupled with the conservation of energy will actually provide us with a very nice tool for analyzing the motion in a central force field of a particle, both qualitatively and quantitatively. But before we go there, let me stress a point. In fact, I don't even think that this point should need any stressing. However, it does seem that some students have a lopsided idea about the notion of energy conservation. So let me point out that energy conservation is not really an independent law of physics. In particular, for this situation, all we could have done is started with the equation of motion, mu r double dot equals minus du dr plus L square by mu r cube, where all we have done is recognized that the force, being conservative, can be written down in terms of the negative gradient of a potential energy term, and for a potential energy term which depends only on the distance r, the negative gradient only has a radial component and is given by minus du dr. We start with that and we integrate this after multiplying by r dot. And then we will end up with the conservation of energy statement that we had. So the conservation of energy statement really is a consequence of the second law of motion. It is not an independent law. This is why energy is often called one of the integrals of motion. With that out of the way, let us now turn to the question of exactly how much information we can glean out of this notion of conservation of energy, especially with the help of this effective potential. To see this, let us begin with a typical potential as an example. This is an attractive potential, could be of the form minus k over r to the alpha, where alpha is between 0 and 2. Our very important example of the Kepler potential minus k by r definitely falls within this category. The exact nature of the potential is not that critical for the analysis, however. It's more the qualitative nature of the potential that we are aiming at here. Here, we have plotted the potential curve in magenta, that's the u of r. L squared by 2 mu r squared, the centrifugal potential barrier term, is the line in green here. Of course, here as r goes to very small values, L squared by 2 mu r squared will become very, very large. U of r will become rather small, in fact very small, or rather have a rather large negative magnitude. However, this restriction that we have here, that alpha is less than 2, tells us that L squared by 2 mu r squared diverges towards plus infinity faster than u of r diverges towards minus infinity. That is actually the important point here, not really the precise nature of the potential. As a result, for very low values of r, it's L squared by 2 mu r squared which dominates, and therefore in the sum of the two, which gives us the effective potential here, the one in light blue, the effective potential rises rapidly like L squared by 2 mu r squared when r is very small. On the other hand, when r is very large, the 1 by r square nature of this potential makes this die down faster than u of r does, and u of r is negative but larger in magnitude for large r, and therefore for very large r, u effective r, the sum, will also be negative and fall off to 0 but slower than the centrifugal potential barrier term. So it's going to be very, very large and positive for small r, small but negative for large r, and that shows that it must cross 0 somewhere and then turn upwards until it tends to 0 as r goes to infinity. So there must be a minimum somewhere in between. We have indicated the position of the minimum, the value of r at which you have a minimum, by r0. And the value of the minimum is u effective minimum. We could have also called this u0, I guess. Now with this setup, let us take a look at a typical situation. Let's say we have a particle which has 0 radial velocity at this particular point. That does not mean that the kinetic energy is 0, however. The kinetic energy, remember, is actually a sum total of two terms, half mu r dot square plus half mu r square theta dot square, which actually is equal to L square by 2 mu r square. Since the L is a conserved quantity, at this particular point, the particle will have an angular velocity and therefore some kinetic energy. But if you just look at the half mu r dot square term, which we are going to call the radial kinetic energy, that's 0 at this point. Remember, our total energy is a sum of this half mu r dot square term and the u effective at r. So at this particular point, this term vanishes. U effective r, which is this, is exactly all of its energy. Now, as the particle moves, this energy should stay constant. That is why the energy has been indicated by this orange horizontal line here. Now, what happens to the radial velocity at subsequent instants? The particle will actually turn towards the left, or strictly speaking, not really the left, inwards. And as it moves inwards, I'm talking only the radial motion here, the gap between its effective potential energy, which is here, and the total energy increases until it reaches R0. So from this position, which we have indicated by R max, as it comes this way, until it reaches R0, R dot actually keeps on increasing in size, although it actually decreases if you take its sign into account. After this point, the particle is going to keep on slowing down in its radial velocity. Remember, all of this is about the radial velocity. And at this point where the E intersects the U effective again, the radial motion comes to a halt because r dot is exactly 0 here. After this, the particle turns back radially and moves outwards, speeds up until it reaches r0, slows down until it reaches back to this position, which we have now indicated by r max. So the radial motion of the particle is going to be confined entirely between these 2 points, which we are going to call the turning points of the radial motion. So most of you who have done an analysis of one-dimensional motion using potential energy curves would find this pretty familiar. The only thing you have to remember is that whereas in one-dimensional motion, a particle is truly at rest at the turning points, at least momentarily, here the particle is only at rest radially. The radial component of the velocity vanishes here and here. The cross-radial component is always non-zero as long as there is a conserved non-zero value of the angular momentum. And in fact, you can also talk about the angular velocity in terms of this diagram. Remember, the L square by 2 mu r square term is actually equal to half mu v theta square, where v theta is the cross-radial velocity, or in more familiar terms, half mu r square theta dot square. So, as the particle moves radially from here to here, the increase in this centrifugal potential barrier shows that as you're moving this way, v theta is actually going up. Indeed, theta dot is going up even more rapidly because along with v theta going up, you have r going down. So the cross-radial component of the velocity increases as you go this way and decreases when the motion turns radially and goes back out. Of course, this is nothing but a direct consequence of Kepler's second law, or the law of constancy of areal velocity, which we have already seen is a direct consequence of angular momentum conservation. One point has to be borne in mind, whereas the radial velocity actually changes direction, so r dot or Vr is negative when it's going from r max to r min and positive when it's going back again, theta dot does not change sign. That's simply because changing sign would have meant that somewhere in between theta dot would have to become 0, but that's not possible because you have a non-zero value and non-zero constant value for L square. So as you can see, this diagram actually gives a pretty nice qualitative view of what kind of motion you will have. The radial motion will be confined between r max and r min, and the cross-radial motion will always be in one direction, speeding up as the radius decreases, slowing down as the radius increases. One important point is the energy considerations cannot distinguish between an orbit which goes like this and an orbit which goes the other way like this. As long as they trace out the same trajectory, the energy considerations that we are using here, since they depend only on the squares of the velocities, cannot really tell us which way you are going. Similarly, at this particular point of the trajectory, you can say that the radial velocity's magnitude will be given essentially by this gap. Of course, this gap is half mu r dot square, but that again gives you only r dot, doesn't give you whether you are going this way or that way. With that in mind, you can still figure out that a huge amount of information about the orbit can be gleaned from this diagram and this diagram alone. Now, Note that when we started, we said that if you start with 0 radial velocity at this position, the particle subsequently has to move in radially, cannot move out. And that's obvious, because if it were to try to move out, the effective potential will be bigger than the energy, which would have led to a negative value for half mu r dot square. And that, of course, is not possible. And by the same token, once it has reached this point, it cannot go any further in, because that again would have led to a negative value for half mu r dot square. So the particle keeps on moving, as far as the radial motion is concerned, in between these two turning values. If, on the other hand, you had a particle which is radially at rest at r0, that is, a particle whose total energy is given by this line here, then it's easy to see that its r can neither increase nor decrease. You will reach a situation of negative half mu r dot square in either case. And that means that for this particular situation, r must stay fixed at r0. That, of course, means that we have a circular orbit. Once again, note the contrast between the one-dimensional case, where a particle being at rest at a minimum of the potential would mean that the particle would be at rest there forever, unless it is disturbed, of course. Here, a particle being at r0, the minimum of the effective potential, means that the particle is radially at rest. Here, a particle being radially at rest at r0 does not mean that the particle is at rest. It just means that the particle will have a fixed value of r as it moves. So it will move in a circle with a center of force as its center. It's also easy to see that it is impossible to have an energy below u0, because if that were the case, then half mu r dot square would have to be negative throughout. Something which is simply impossible. Of course, the motion does not always have to start with radial rest, that is, with r dot 0. For example, suppose the particle is here at a particular instant of time and it has a non-zero r dot, let's say to the right. In which case, this value, of course, gives you just the effective potential, but to that, you have to add the half mu r dot square to get the total energy. And the total energy then would be something like this. So the particle, which is traveling radially outwards, will keep on moving radially outwards, but its radial velocity will slow down until it hits this point, that is, gets to this position here, which is the r max for this current motion. It will then turn back and go all the way until it gets to this point, and then keep on going in between. So once again, you will have a bound orbit with r max and r min being the maximum and the minimum value of the radial distance that the particle achieves, and the cross radial motion will be as described before. Slowing down when you are far away from the center, speeding up when you are closer to the center. Now let us consider one more situation here, where the particle starts out at, say, the same point, but now with a very large speed, maybe a very large speed inwards, radially inwards. Once again, I'm talking of only the radial speed right now. So large, in fact, that the half mu r dot square is big enough to change the total energy to a positive value. Let's say the total energy is somewhere up here now. Half mu r dot square is this big gap. Then the total energy will be given by this horizontal line. So now you have a case where E is positive. Let us try to see what will happen to the motion now. Let's focus only on the radial motion. The cross radial one will take care of itself by Kepler's second law, or by looking at this L square by 2 mu r square graph, as we explained before. Since the particle is moving radially inwards at this stage rather rapidly, it will keep on moving inwards. As it moves inwards up to r0, its radial velocity will keep on increasing in magnitude. So the particle will speed up until this point radially. Then it will slow down, come to a halt, again radial halt at this point. and then turn back again. But now as it keeps on moving radially outwards, it will not meet another turning point and it will go off to infinity. So this gives us an example of an unbound orbit. All the other possible orbits that we had talked about before this, orbits for which the total energy was negative, that is, was less than the value which the potential has at infinity, were bound orbits. They had multiple turning points, in particular 2 turning points. So the motion kept on, at least in the radial direction, between a smallest value and a largest value. Here the motion has no upper bound as in the radial direction. The particle can go far, far away from the center without any upper limit. Of course, as it moves further and further out, its cross-radial velocity and angular velocity will keep on going down. But the radial velocity, which will also decrease, will still stay finite even at an infinite distance. Now, specifically, if we were talking about the 1 by r potential, then all the previous possible cases we have talked about would have led to elliptical orbits. This is a result which we have not proven yet, but we already know this from our past studies. So we are just using that result. The one exception, of course, is when you start with radial rest at r0. That's really not an exception. It's a special case of an elliptical orbit where the orbit is circular centered at the center of motion. On the other hand, if a particle has positive total energy to begin with, then the Kepler orbit would be unbound, and that is the hyperbolic orbits which some comets, for example, one-time visitors to our solar system can have. And the limiting situation where the energy is just 0 gives us a parabolic orbit. Once again, let me stress that these special shapes, the elliptical, parabolic, hyperbolic, are specific to the inverse square force law or minus 1 by r potential. The qualitative nature of the orbits for other potentials in this category will also be similar, though the shapes of the orbits would typically be more complicated, and indeed none of these orbits, as we will see later, will be closed in general. This picture shows you a plausible trajectory for a particle moving under a central force field of the kind that we are discussing right now. For the particular conditions that you have, that is for the given value of L and E, the largest possible distance radially would be given by this R max and the smallest by this R min. And in order to sort of illustrate that, we have drawn 2 circles to signify the largest and smallest distances from the center. The particle is starting to move from here and going on outwards until it hits a maximum radial distance, then turns back in, and at this point, of course moving much faster cross-radially, it gets to this position where it hits R min, then keeps on going. But when it returns to R max again, it's not at the same point, and so the orbit is not really closed. This keeps on going in a rosette-like structure. Now, in addition to these distances R max and R min, I have also indicated by these dashed lines, the blue line here and the magenta line here, the rather small magenta line here, 2 specific points or 2 specific directions in the picture. This point is called the apse of a curve, a point where it is at its maximum distance from the center. Another apse is this one, where it is at its minimum distance. So, what you have here is one apse, then onto another, then of course you have further apses, this one is another one, then it comes to another apse which is close to this one, and so on. Now, the angle between these 2 apsidal lines, that is going to play a very important role later on in deciding whether this orbit can at all ever be closed or not, and also in figuring out under what situations will a potential admit of closed orbits. We will discuss this in a later lecture, but for the time being, let's just point out that these two apses define apsidal directions, and the angle between them is what is called the apsidal angle theta A. In fact, it is pretty easy to figure out that if theta A divided by 2 pi or equivalently 2 pi by theta A were rational numbers, then the orbit would be a closed one. Let me just state at the stage that this is a very special scenario, and for most potentials, as we will see in the next lecture, closed orbits are a rarity. To quickly summarize the situation, what we have seen is the following. If the energy of a system is equal to the minimum value of the effective potential, then radial motion is not possible. The orbit will only be a circle with radius r0. For slightly larger energies, the radial motion oscillates between Rmax and Rmin, between two turning points. These points in space where Rmax and Rmin are achieved are the apses, and the motion may in general be unbounded for larger energies. Before I go on to repeat the same kind of analysis for different categories of potentials, let me talk about a particular topic which is at the same time amusing and somewhat scary. The topic has to do with a very, very well-known textbook. I'm pretty sure most people who have studied advanced physics at any level would be familiar with this particular textbook, and the cover, which you can see on your screen right now, should be very familiar to many people. In fact, the picture on the cover is basically a picture taken from inside the text. This is figure 3.7, a picture from the textbook by Goldstein and some other co-authors who joined later on, this famous textbook of classical mechanics, and this is in the chapter on central force fields. In fact, it was sort of implied, though not expressly stated, that this is the kind of orbit that you would have in an attractive potential. Now, as you can see, you have a R2, which is actually our Rmax, and an R1, which is our Rmin, and you have the apsidal line here and here, at least two of the apses, neighboring apses, and this of course is the apsidal angle. So everything looks all nice, and the particle is supposed to travel like this. Now this actually survived in the textbook and also as a cover of a particular edition for a rather long time before people spotted that there is a problem with this. And the problem actually is pretty simple to figure out if you think about it. If you focus, for example, on this part of the curve, can easily see that the force acting on the particle is actually inwards. After all, we already know that force is radial and it's attractive, so it has to be inwards. But let me just point out that you didn't even have to know that. Just from the figure, you should be able to figure out that as long as you have a particle moving in a curve like this, if you look at this small section, it's almost like a motion in a circular path. I've shown the full circle with dots here, and a particle as it travels in that path has an acceleration towards the center of the circle. So here the particle is clearly accelerating in this direction, which is all fine. But notice what is happening at the other apse. There, the circle-like thing that you can think of in terms of trajectory is actually this one, and the force on the particle at this point is clearly pointing towards the center of that circle, which is outwards. So the motion that has been depicted here is just impossible for bound orbits in an attractive potential. Now, To their credit, what the people behind the book did after this was A. change the cover, and B. even change the figure. Also, if you look at newer versions of this edition, which has an erratum at the end, you will find that they clearly say that this particular kind of motion is not possible for a purely attractive potential. Of course, it is possible. Nobody is saying it's impossible, so it's not real an error in that sense. But such a motion would be possible if you had a potential which had an attractive part, which is stronger at larger distances, and a repulsive part which is stronger at smaller distances. Then, of course, you could explain how the particle happens to be accelerating inwards at the outer apse, the apocentron, if you just use the standard technical sounding term for this, and accelerating outwards at the pericentron. Closest to the center, that's the pericentron point, and here is the apocentron point. This inward acceleration and outward acceleration can actually be explained away by assuming that you are actually moving in a potential which has this particular character. If you read the book carefully, nowhere does Goldstein actually say explicitly that this orbit is only for an attractive potential, so this may not really have been an error, except for the fact that this was in a section which was talking about an attractive potential. So, if not exactly that, Goldstein did seem to imply, at least most people thought, that this would be in the orbit for an attractive potential. And as we have just seen, that is clearly impossible. And the argument that told us that this is impossible does not really have anything to do with central forces. This is just simply the fact that if you are moving in a curve, you would have a force towards the instantaneous center of the curve. Of course, if you were moving with a time-varying velocity, you would also have a motion tangential to that, which is something you cannot have in a central force field, at least at this and this point, simply because here the tangents are really in the cross-radial direction, here and here, not elsewhere. So, because the cross-radial component of the force is 0, at this point at least there is no tangential acceleration, neither is there any cross-radial acceleration here. Now, again, to their credit, not only did Goldstein's current maintainers change the cover, they also changed figure 3.7. Now you have a curve which goes like this, which is a possible curve. In fact, it's possible for a potential which is proportional to r to the power 7. You can also see that this is a closed curve, which is a bit of a pity. A potential of this kind, proportional to the r to the 7, would actually lead to a closed curve like this for very special initial conditions. But for this, very, very commonly what you would have is that the curve would not be closed. In fact, closed curves are a rarity, except for two specific kinds of potentials. So, frankly, the original cover of Goldstein, while not showing an orbit which is feasible for a purely attractive potential, did show an orbit which is of the more common kind than not. In contrast, the cover of another textbook, very famous textbook, that by Marian and Thornton, called Classical Dynamics of Particles and Systems, did have, at least one edition did have, a figure of this kind, which is perfectly alright as far as structure is concerned. This is a very possible non-closed orbit for an attractive potential. This looks very much like the kind of orbit that we talked about a while ago. Now, please don't assume that I'm actually rooting in favor of Marian and Thornton and saying that Goldstein is not a good book. Nothing of that kind. Both books are actually very, very good. And depending on your preferences, one or the other may suit you. Both have very good descriptions of the topic of central force field motion, though not a complete description. So this is not a vote in favor of one textbook or the other. I just wanted to point out that even a very famous, well-known textbook like Goldstein got some of the things, if not exactly wrong, let's just say not quite right, which should tell you that you have to think very, very deeply before you feel that you really understand what's going on here. With that warning firmly in place, let us now move on to the other categories of potentials that we have not mentioned yet. For example, one of the categories we could think about is an attractive potential of the form minus k by r to the alpha, but here alpha is bigger than 2. What that means is that when you come to very small values of r, the potential will fall off to negative infinity much faster than the centrifugal potential barrier L square by 2 mu r square will shoot off to plus infinity. As a result, the effective potential can have a peak somewhere, but then it will drop off to minus infinity as you reach towards r equal to 0. Now, a very similar analysis can be carried out, and I will just highlight the results here because they should be very easy for you to figure out. If you have a negative E, something like this, it's obvious that a particle can only be somewhere here, not here, because here the energy is less than the effective potential, leading to a negative value of half mu r dot square. And as we have seen over and over again, that's simply not possible. So the particle for such a case, for this particular energy, has to be somewhere in this region. In fact, this point at which the energy catches up with the effective potential is a turning point. So if the particle were moving outwards, it would hit the barrier, so to speak, and then turn back, but then collapse to r equal to 0. So eventually, the particle will definitely collapse to r equal to 0, irrespective of whether it was moving outwards or inwards when we first met it. Now, if the peak of the potential happens to be positive, and our energy is actually somewhere between 0 and this peak u0, then a somewhat different scenario occurs. Now you have two turning points once again, but the behavior of these two turning points is very, very different from the behavior we had seen before. Here the particle definitely cannot move in between the two turning points, unlike our previous case, because in between the two turning points, the energy would be less than the effective potential. So the only possibility is the particle could be either here or here. If the particle happens to be here and traveling, let's say, towards r equal to 0, it would come towards this, slow down, come to a halt. I'm talking once again only of the radial motion here, and then it will just bounce off to infinity. So if the particle is somewhere here to begin with, its ultimate fate is to land up at infinity. On the other hand, if the particle happens to be here, then if it were moving to smaller r's, it would just fall into the center, collapse to the origin. Or if it was moving outside, then it would hit the barrier, turn back and fall back at the origin. Finally, we come to this kind of energy level, which is bigger than u0. For such energies, there are no turning points and the particle will ultimately always fall to 0. If it were traveling leftwards, or go away to infinity if it were traveling rightwards. So three kinds of motion. Just to summarize, for negative E, you always have collapse to r equal to 0. For positive E, you either have collapse to r equal to 0 or escape to infinity depending on which way the particle is moving initially. And for energies between 0 to u0, it's always either escape to infinity or collapse to 0, but this time depending on which side of the u effective r hill the particle happens to be, not on which way it is moving. Let's take a quick look at another case. This is again an attractive potential, but here it's a potential which increases with distance, a potential of the kind kr to the alpha. Although remember, this is just the kind of behavior we are looking at, not necessarily the exact potential form. It is the basic behavior which is of importance, and here alpha is positive. For this, you have a potential which keeps on rising off to infinity. This is the actual potential. The L square by 2 mu r square rises up to infinity as r goes to 0, and so the effective potential, the sum of the two, basically goes like this. It goes through a minimum, then rises up to infinity on both sides. So in this case, all orbits, no matter how high the energy, are bound orbits. You always have two turning points. Well, I'm drawing them here on the curve, but actually they're down here on the r-axis. The particle always keeps on oscillating between them, a large r and a small r. Of course, once again, we are talking of only the radial motion. And the motion, as we have already said, is always going to be bounded. Finally, we come to an entirely different kind of potential, and a repulsive potential. Say a potential of the form plus k by r to the alpha. The kind of potential, for example, an alpha particle approaching a positive nucleus would feel. Of course, for that, alpha would have been just plus 1. That would give you k by r potential. So here you have the actual potential. This is the centrifugal potential barrier term. The sum is like this. No minima, you only have a single turning point. And for example, if this is the energy, the particle simply couldn't be somewhere here, had to be somewhere here. If it were traveling towards r equal to 0 from this point, it would come, hit the barrier, so to speak, and turn back from this point and then off to infinity. If it were already traveling outwards, it would keep on traveling to infinity. So here all orbits are unbounded. I'm sure that by now you are pretty convinced that you can gain a lot of information, especially qualitative information, about the nature of orbits from the notion of effective potentials. Actually, there is a lot more to it than that. You can do a lot of quantitative stuff as well. We will discuss them in detail in the next lecture. However, let me just give you a quick glimpse of the kind of things that we can do. For this, let us go back to the kind of potential that we had at the beginning. That is a potential which was attractive, of the kind minus k by r to the alpha, but alpha was not bigger than 2, so that the potential actually went up to plus infinity. This is the effective potential I'm talking about, as r goes to 0, and went off to 0 after going through a minimum as r goes to infinity. Now, in such a case, we saw that you have circular orbits for energies which exactly coincide with the minimum of the effective potential. This happened at a particular radius r0. The question is what happens at nearly circular orbits, that is, when r is very close to r0. Now, one thing that we can always do in such a case is expand the effective potential u effective r in powers of r minus r0. This is the simple Taylor series expansion, where you get u effective r0 as the first term, then you have u prime effective r0 r minus r0, plus u double prime effective r0 by 2 factorial into r minus r0 whole square, plus higher order terms. But now note that u effective r0 is essentially just a constant, which really doesn't have much to do with the dynamics. U prime effective must vanish at R0 because R0 after all is a point where U effective is the minimum. So the non-trivial lowest order term is really this one. And when R is very close to R0, that is R minus R0 is pretty small, the higher order terms can be safely neglected. So U effective R, after you neglect the higher order terms, simply becomes this constant non-dynamical piece plus this quadratic piece. And so our equation for conservation of energy can simply be rewritten in this form: half mu R dot square plus U double prime effective R0 by 2 into R minus R0 whole square. And on the right hand side, you have energy minus U effective R0, some constant. Note that this is exactly the kind of equation you have for a harmonic oscillator in one dimension. Only the center of the harmonic oscillator here is not at R equal to 0, but is at R equal to R0. So this means that at least as far as the radial motion is concerned in this case, you will have oscillations about R equal to R0, which is something very familiar to us from the theory of small oscillations that we have studied for one-dimensional motion. Now, if instead of this you had a maximum in the effective potential, even then, right at the peak, you would have a circular orbit, but that circular orbit would be unstable. A slight displacement to one side or the other will take you either to R equal to 0 or to R equal to infinity. That was the case with our second potential. But as long as we are talking of a potential which leads to a minimum, in U effective R at R equal to R0, you have U double prime effective R0, which is positive, and the radial motion is approximately then simple harmonic with a time period which is given by a very, very familiar formula. The formula which says the time period for the radial oscillations is simply given by 2 pi divided by the angular frequency, that is 2 pi times square root of mu by U double prime effective at R0. In our next lecture, we will start with this expression and try to show you an argument why you would expect closed orbits, at least for initial conditions which do not vary too much from those for circular orbits, for the potential minus constant by R, that is the Kepler potential. But this formula is just the tip of the iceberg, really. We can get a lot more information, quantitative information, out of the notion of effective potential. That will essentially be our topic for the next lecture. Bye till then.